All right, moving on one layer up is the routing issue in ad hoc networks. And this slide does talk about what we need in a routing scheme, and then we talk about the 3 routing schemes next. But going through the issues first, the routing is fully distributed, and if we keep knowledge of everything on the network, as we do actually on the wired network, we keep knowledge of everything on the network and keep it up to date, that would be very, very expensive, because first of all, the network changes very fast, and the second thing is every message requires lots of bits, and bits are very expensive in wireless networks. And then they have to be transmitted over several hops, so they become even more expensive. So generally what we do is we keep a very localized information. So I just may not know the whole network, I may just know my neighbors, but when the need comes in, we can quickly construct a route from just knowing the neighbors. And we talked about the loop-free routing. Is that and this is not special about the wireless, but in general we need to make sure that if there are any loops in the network, the loops are broken up so that the packets don't just keep circulating in those loops. Minimize the route acquisition delay, so that is a proactive routing where you keep the route ready almost all the time by exchanging routing information, and then whenever somebody needs to send something out, we have a route automatically available very fast. So that is how we minimize the acquisition delay. Quick route reconfiguration, because of the changes, because of the moves of all the nodes, we have to basically update the databases. And the key is that we just really need to know more about the local networks than about the remote parts of the networks, because there could be a lot of things that could be happening in the remote part that do not really affect our local traffic, and therefore we may not need to know that. So as opposed to in a wired network where we generally send information regardless of the distance, in this ad hoc networks we may not want to send the information simply because it is more than one hop away. All right, then energy conservation, we talked about that. So we have to worry about how often people sleep and how they're woken up. And then unidirectional link support. And this is the same asymmetric link support we had talked about in the satellite networks, where you have data coming in on the wireless but going out on a telephone dial-up line. So that is another issue in ad hoc networks. So our goal actually in routing is to minimize the number of hops. Basically what we want to do is all the bits that are transmitted from all the nodes divided by the bits that are delivered. We will find that for every one packet delivered, there are 5 packets that have been transmitted, because packet might go over 4 or 5 hops. At each hop there is a packet transmitted. So the ratio of the two is called the average, is actually the average number of hops, and so that's the critical, is that we really want to find routes that don't use too many hops. Second issue is that of the overhead. And overhead is measured in 2 different ways. One is, basically there are 2 sources of overhead. One is the header bits. Those are called control bits. And sometimes in IP, the header bits could be, quite large, like 40 bytes of a header. And the data bits, if they're small, then this may not be a good match. And the control packets and the data packets. And second thing is that there could be lots of control packets, such as routing messages going around, or any other thing that is required to set up the connection. Those are all control packets, and they are just part of the overhead. And so one has to have to minimize the control in any scheme they develop for wireless. We'll move on to the routing schemes. Again, as I said, there are whole chapters and books devoted to ad hoc routing. What I've done here is just summarize the key ways people classify their routing work, And the first way to classify would be, when is the routing done? By routing I mean, when is the route list prepared? And this could be a proactive, which means before it is needed, you already have all the routes stored in your office or in some place, so that whenever somebody needs to go from A to B, you look up the table and say, oh yeah, right, you can take this flight, direct flight. Whereas reactive means that you do that only when somebody asks for you. Somebody says, oh, I need to go from A to B, what do I do? Then you go ahead and do some routing messages with other nodes in your neighborhood, and then you figure out that what is the best way to get there. So that is on demand. And hybrid is which combines both. Then comes the temporal information. So whether we use the past historical knowledge or not, how long old we can use depends upon how fast the network changes, and how obviously the nodes have their own lifetime, and so depending upon where they are located, they could go up and down, and so that's another issue. Another way of classifying is whether, what is it based, how much prior information does it need. Topology organization, whether the addressing should be flat as it is in 802.11 or 802.3, or should it be hierarchical as it is done in IP and other places. And hierarchy could be geographical or by hops. Resource optimization, we talked about power awareness, and then the next thing is geographical information based. Is that people who are close by and who are away, people may have a different way of sending packets. Basically, is that obviously you don't want to send to people who are too far away. At the same time, you don't want to always overload the person who is just next to you. And efficient flooding. So many times, as we will say in the next few slides, one of the applications of ad hoc wireless in the disaster, and the disaster situation, we generally need to have multicast and broadcast. So these broadcasts have to be very efficient. How do we do efficient broadcast? And flooding is actually just an excessive broadcast. Now, if you wanted to see routing algorithms, there are 40 and more routing algorithms mentioned in this chapter of the book that we followed last time. We are going to talk about just 3. Now, before I move on to routing schemes in wireless networks, I thought it would be good to review how the routing is done on the wired networks. So this slide does that. It says routing in the wired networks. In the wired networks, the routing schemes are classified into 2 categories. Either their distance vector or their link state. What is a distance vector scheme? In distance vector scheme, each node sends its complete table. Each node computes the distance to all possible nodes in the network, and its complete table, it sends it to its neighbors. Alright, so there are a lot of information which is sent, but it is sent only to few people. In the link state, each node sends its information about the neighbors to the entire world. So basically you have very small amount of information, because all you are telling everybody is that node A is 3 milliseconds away from me, and node B is 5 milliseconds away from me. So you just tell out your neighbors. So this is very small information, but you tell it to the whole world. So the question is, which one is better? Distance vector or link state? And now we could argue either one to be better, because probably the total overall number of bits times the number of hops is same in both of them. But in general, link state schemes are considered better and more recent than distance vector schemes. And that's why basically in our IP protocols, OSPF actually is a link state protocol. And that's very common. And so going back again on the distance vector scheme, Generally, they might have taught you in 473 the Dijkstra's algorithm. So Dijkstra's algorithm is used to compute the shortest path, and then everybody just uses the shortest path. The RIP protocol is a distance vector protocol. So RIP is the routing information protocol, which is used along with OSPF, and that's a distance vector protocol. So it uses exactly what we said here, is that it takes the complete table, the distances to all the nodes, and we send it to the neighbors. So big information to a small set of people, or link state where we take small amount of information to a large set of people. We send it to the whole network. So that is the link state. Small vectors to large number of nodes, and we use an algorithm called Bellman-Ford's algorithm to compute the shortest path. Alright, so then we can go into link state and so on and so forth now, because we are going to use these words in wireless. So one of the first protocols that was considered at IETF is OLSR, Optimized Link State Routing Protocol. So from the keywords we already have is optimize and then the link state and routing, right? So it's a proactive algorithm, and proactive means what? We had two, remember we had two kinds of routing algorithms we talked about today earlier in the lecture: reactive and proactive. Reactive actually protocols are the ones that generate the route whenever they need it. So they generate the route after somebody says I want to get there. Whereas proactive ones will keep the route prepared so when somebody wants to use it, the information is always there. And the idea is that if you keep the information always ready, then you might have too much overhead. So that's where the word optimized comes in. Is optimized means that whenever a new information is sent out for broadcast, so only the subset of the nodes need to be told, and so that way we minimize the overhead. So I might have 5 neighbors, but I will not tell all 5 neighbors about every single change on my network. I might just send to 2 neighbors. We know these 2 neighbors are very highly chatting nodes. They talk to a lot of people, and they will certainly spread the information. So we call them multi-point relay, or MPR. So this is the key, OLSR, and please listen carefully to this particular part of the lecture because the homework is related to MPRs. And so if X is your MPR, so what happens is every node selects a subset of its neighbor, which it calls MPR. So if X is your MPR, then you are X's MPR selector. You are the selector, and the node X is the MPR, right? Each MPR has a set of MPR selectors. So each node which can be called MPR actually has a set of nodes that have selected it. So those are called set of MPR selectors. Each node sends their LS to all its MPRs, not to all neighbors. Each node sends LS to all its MPRs, and then the MPRs forwarded to their neighbors. So other neighbors, other network neighbors use information to compute routing tables but do not forward. So you might have, let's say, 5 neighbors, and 2 of them you have selected as your relay nodes. So yeah, actually maybe the previous statement was correct. I'm sorry, I should not have corrected that. Is that you send it to all of them, but only the MPRs are the one that forward it. Other nodes do not forward it. So the issue was about forwarding, that only MPRs will forward it. So you have 5 neighbors, and 2 of them will forward to the on, and the rest of them, 3 of them, they are not MPRs. They will just use it themselves but not forward it to anybody else. So you really send to all 5. So OLSR significantly reduces the LS control traffic. So by not sending to all 5, you have reduced the control traffic quite significantly, because in this example that we have been talking about, at least 3 nodes don't have to do any more forwarding and no more of the overhead in that case, whereas only the MPRs will send it. So in general you might send as many few messages as there are MPRs. So basically if you have 2 MPRs out of 5, you might send 2/5 messages as compared to sending it to all 5 and all 5 forwarding it to their neighbors and their neighbors forwarding to the rest of the neighbors and so on and so forth. So RFC 3626 talks about OLSR version 2. So now let's see. Actually, we have an example that makes it clearer. So I am going to hold on to the questions until this example is done. So here is a node 5, which wants to send the routing information to the whole network, right? So 5 has total of 7 neighbors. We can see that 2, 3, 4, 6, 8, 7, and 11. Those are its neighbors. And it has selected 4 and 8 as MPR. So 4 and 8 have a special status because they have high connectivity. The 5 has selected them as their MPR. So it sends, whenever it wants to send the information, it sends to all 7. It sends to 7, 11, 2, 3, 4, 6, and 8. But only 4 and 8 will transmit them further. So 8 will send it to 9 and 10. And 4 will send it to 1, 13, and 12. Alright? And as soon as the 4 does that, basically every node in a network has gotten the information that we needed to transmit. Okay, so by just sending from 5 to 4 and 8, we are able to cover the entire network. So that's the whole idea behind OLSR. When they do this routing, after the routing is done, they also do the cleanup. Key issue is how do you select your MPR? So there are 5 neighbors, but we selected 2 neighbors which as their MPR, and I will first give you a brief introduction here and then describe more formally in the next slide. So 5 has selected 4 and 8 as its MPR, and it has not selected the other nodes. Why? Well, the other nodes don't have that much connectivity. For example, 3 has only 2 links, 1 is to 5 and 1 is to 1. So obviously it is not a highly connected node and doesn't really talk that much to its neighbors, right? Whereas 2 has 3 links, it has 1 to 5 and then 11 and 1. 7 has total 3 links, and 4 has 5 links. You see, 4 has 5 links, so 4 is really a good MPR because it has a lot of connectivity. So we really, among our neighbors, we look for ones that have very high connectivity, and if they have very high connectivity, we take them as MPR. So 4 and 8 are actually MPR of 5 for that reason. So what you do is, if you use very large number of nodes as your MPR, then you are going to increase the overhead, right? So your really goal is to minimize the number of MPRs. And basically the goal is to get the smallest set that will cover all 2 hop neighbors. What is a 2 hop neighbor? Anybody that I can reach in 2 hops is my 2 hop neighbor. So for example, let's go back to this and let me ask you, who are the 2 hop neighbors of 5? Anybody? Can anybody recognize the 2 hop neighbors of 5? That's a good number. So those are the 2 hop neighbors. The rest of them are 1 hop neighbors. So we call them N1X and N2X. N1X is the set of all the 1 hop neighbors. N2X is the set of all 2 hop neighbors. So we need to, among the N1 sets, we need to select MPRs. So we need to select the nodes that can cover as much of N2 as possible, right? So what we do is we start with N1X, which is the set of all the nodes, and we start with MPR of X, which is the null in the beginning, which could be a null in the beginning. So basically N1 minus MPR is actually N1 itself because MPR is null. So this is a set algebra here. We are taking the N1X, which is the set of all the 1 hop neighbors, and we remove the nodes that have been selected as MPR. and from the remaining node we find out what is the connectivity, and we select the node that has the maximum connectivity, and we say, okay, you have lots of connectivity, I want to use your node as an MPR, and so you do that. Once you select them as an MPR, then you go back again and then delete the neighbors that have already been covered. So now your N2X will reduce because you have already covered many neighbors by the first MPR. And then now you do the same thing from N1X minus MPR, which you start with a null set. You find out which particular nodes have been covered or not covered. Okay, so here's the key question. Basically, first of all, I think there are three things here we talked about. First is the OLSR. Is it clear as to how OLSR works? And then second question is, are there any questions about how to get MPRs, how to select MPRs? So what happens is, it works the same way, basically recursively. Each node has its MPRs. And so 8 might have its own MPRs, for example. So 5 sends it to only 4, and it sends to all of its first hop neighbors, but only 4 and 8 transmit it further. When 4 and 8 transmit, they have to decide the same way. They have to basically have their own MPR, and then they will select it further only to 1 or 2 neighbors they will send. They will send to all their neighbors, but only their MPR neighbors will send it further. So, and this whole process continues all throughout the network, and that's why it is called optimized LSR, optimized linked state routing, because you are really not sending it to the nodes that really not adding any value to what you want to do. So 4 and 8 actually cover the entire network. So for example, in the example I gave you, suppose 5 sends it to 2, 3, 4, 6, 8, 7 and 11, which are all its neighbors. Alright, so it has sent 7 copies to 7 nodes. After that, 4 can send it to whom? Who are the 4 neighbors? Yeah, 1, 13, 6 and 12. So that will be covered by 4. Then some of them will transmit if there was a bigger network, right? But let's continue with this network. 8 will do what now? 8 will send it to whom? No, 8 will not send it to 12. Why not? Yeah, it's not directly connected. Okay, so that is one thing. But it will send it to 6. So 6 might get 2 copies. Well, so hold on. Yeah, it will send to 6 unless there was some more negotiation in which 5 somehow tells 8 that 6 is my neighbor and that I've already taken care of it, so you don't have to worry about 6. So there might be some more optimization that can be done. But 8 will certainly send to 9 and 10, and once it sends to 9 and 10, then everybody in the network is covered here. Now the question was asked, what if there is a third layer of nodes? Yeah, so it will continue the same way. I mean, basically 8 has sent to all its neighbors, and then some of these neighbors have been selected as MPRs. They will forward it one more hop. Others will just keep it. Does that answer your question? Okay. Alright, so now the homework actually is about selection of MPR. And selection of MPR is basically, as I said, let's see. Selection of MPR is basically based upon connectivity. So you first list all the neighbors, and then you list where they can reach. So 2 can reach 1 and 11, 3 can reach 1, 4 can reach, whatever, and you write it down. Then you select the node that has the highest connectivity, and you put it aside, and you take out all the nodes that have been covered by that. So for example, when you select 4 as the MPR, you remove 1, 13, 12 from further consideration in N2, because you make the list of N2 nodes, which are the 2 hop nodes, and you want to cover all of them. So first you find out which one can do most, and the 4 can do most, so you select 4 as the MPR, and then among the rest of the nodes, then you select the one which has the highest connectivity again, and so on. So you just have to do that in the homework. Now the question is, can a node select MPR? That would be counterintuitive. The thing is, the MPR's job is to send one more hop. So if the node selects itself as an MPR, then what is it going to do? Every node has to send to one hop to all its neighbors. So it will send it. So every node is going to send to all its neighbors. But the question is which of its neighbors. MPR is only which of its neighbors should send it one more hop. So this is a question about the second hop, not about the first hop. So for the second hop, the node itself cannot really do much. I mean, node doesn't have connectivity to these second hop nodes. I mean, in this example that we have, for example, to reach 13, 1, 12, and 10, I mean, what can 5 do? 5 has the most connectivity as shown here, but it is, I mean, it cannot select itself as an MPR because it doesn't have reachability to the second hop set. And what we are trying to do is we are trying to find the node that has the maximum connectivity to the second hop set. This is a link state algorithm, remember, right? In the link state algorithm, everybody tells everybody who they are connected to, right? So before MPR selection happens, 8 would have advertised that I am connected to 5, 6, 9, and 10. And 6 would have advertised that I am connected to 5, 4, 12, and 8. And 4 would have advertised that I connect. So there is a lot of flooding which is going on before all this happens. During that flooding, everybody learns who is connected to what. So 5 then knows that who is 2 connected to, who is 3 connected to, who is 4 connected to. So it can make a whole list and then select its MPRs. And then it tells those nodes that you are my MPR. 4 and 8 are MPRs of 5. Now 5 could be an MPR for several nodes here. Can you think of the nodes for which 5 could be an MPR? Actually 5 has such a high connectivity that it will be probably MPR for all of its neighbors. 5 has a connectivity of 3 to 4, 5, 6, 7. None of the other nodes have that much connectivity. So when all of these nodes select their MPR, they will select 5. So 2, 11, 7, 3, 4, and 6, and 8, they will select 5 as its MPR. Yeah, so each node has its own set of MPRs, and each node could be an MPR for some other nodes.